Attending. It's my honor to introduce Katrina Ligett. Katrina is a professor in the CS department in Hebrew University, and she's also the director of the Study of Rationality Center. Katrina is very well known in our community and broadly for the amazing work she has done laying the foundation of privacy, algorithmic fairness, her work on theory of machine learning and algorithmic game theory. And she's been a role model to many of the junior, not so junior anymore, faculty and students in this area. So we are really, really excited to have her here and give the Richard M. Karp lecture, and really looking forward to learning more from her today. Thank you, Katrina.
Thank you so much. Thanks for the generous introduction. And thank you to the boot camp organizers for putting together a great program to kick off the semester. Thank you to the program organizers and the Simons Institute for this invitation and for putting together the program of the semester. Having seen the thought that went into an early visioning workshop that sort of led up to this semester and what I've seen of the boot camp so far, I think we're all in for a treat, and it should be a fun semester. So the starting point for my talk is the observation that modern AI just works. AI can write code for me. It can make realistic videos of, I don't even know what that is. It can apparently successfully convince people that it's human. And theory is honestly lagging way behind. And it's not that nobody's trying to do theory of modern ML, and it's not that neural networks don't have a lot of interesting math behind them. They do, and people are very smart people, including people in this room. But it feels like people are struggling to provide very sort of partial explanations of pieces of toy examples to try to understand what works and how well and why. The ML theory that I know doesn't tell me how computationally efficient the code will be that my model will write. It doesn't tell me what that depends on, doesn't have anything to say about whether or not I'll be able to make a photorealistic video of a fat pink fish, or how much compute or data that really inherently requires. It doesn't tell me under what conditions the model that I train will try and succeed at convincing humans that it's human. There's a lot of big questions here. I don't have a theory that answers them. I think we probably need a big new theory. I mean, we have some big puzzles here. We have some basic puzzles here. We have the basic puzzle of how are modern AI models so rich, but yet not exclusively producing garbage. They're rich enough to completely overfit to their training data, and yet they often don't. So probably we need a revolutionary new theory in order to get us to explanations in this space. That's not what this talk is about. This talk is not about revolutionary new theory. This talk is about something much more conservative. I want to do a more conservative accounting to try to chip away slowly, modestly, at little bits and pieces of the gaps that we have between the theory and the practice of ML. That's what we're going to do today. So basically, the thesis of this talk, which I hope turns into being more of a discussion, is that we can already squeeze more, sometimes much more, out of the algorithmic tools that we already have by taking advantage of the properties that our algorithms have that lead to their success, and by trying to step away in various ways from a worst-case perspective, sometimes towards more instance-specific analysis. And the way that I want to do that with you today is I want to walk together through 5 vignettes. This is not going to be a technical talk. This is going to be a meta-technical talk. It's not going to be a comprehensive worldview. It's going to be 5 different problems that give us some perspectives that I hope have unifying themes that are more broadly useful to many of us. I'm going to be talking about the work of lots of other people, including some people who are in this room. But I'll be talking about things that I happen to have encountered in my particular path. And I'll be curious to hear if this resonates with you and if you have other examples that you wish that I had brought. Things to add to this list. There'll be two main themes that run through our discussion today. The first of them is that randomness is everywhere. This is not surprising to any of you. We all know and love randomness and use it in all sorts of ways. We've got random orderings, we've got random subsets, we've got random projections, we've got perturbations of various sorts, of objectives, of data points. Randomness is showing up all over the place in lots of different ways and for lots of different reasons. We use random subsets sometimes to replicate or attempt to simulate the behavior that we might get if we used all of our data, but with less compute. We use random projections to mean distances, but in a compact representation. Randomness helps jump us out of bad plateaus, bad local minima when we're doing search. Randomness makes computations more robust, more stable, more private. It reduces overfitting, and none of this is new, none of this is news. At least since the 90s, maybe even earlier, we've known, for example, that if you noise the input to a neural network, you can improve your generalization performance. None of this message is new. But I want to advocate for really counting every last bit of randomness, to do a careful accounting here, and to try to give it credit simultaneously for all of its good effects at once. I want to exploit the randomness that's already in our processes, in our algorithms, and use it for other reasons. Again, nothing new there. The second theme is that we might not care just about the worst case. Of course, I love the worst case, as many of you do, as much as the next person. It has elegance, it has finality, it has paranoia that suits me just fine. But sometimes the worst case scenario, whether it's worst case data or worst case sequences of computations or worst case whatever it is, isn't what's realized. And maybe what we care about is something that's much friendlier. Or maybe the worst case is just unlikely, or we're willing to tolerate guarantees that only hold in good situations or hold most of the time, which can potentially really improve our results. And again, there's nothing new about this theme, about this message. CS theory has been stepping away in various ways from the worst case for decades. Whether it's looked like average case analysis or smooth analysis, parameterized complexity or instance optimality or whatever category suits you. We've been trying to get away from this in various ways at various times, and also, to give credit where credit is due, some fields never got into this whole worst case thing in the first place. Fields like statistics have never been shy to make bold assumptions about the settings in which they'll be deployed. They're happy to make wildly oversimplistic assumptions about the data distributions they deal with. So again, nothing new here, but just another old theme that's going to come back, I think, big time for lots of reasons today. Okay, so those are my two themes. As I mentioned, we're going to go through these vignettes. It's my own personal sort of path and story that brings these particular stories here. And at times, if you listen to me, you might think that this is talk about privacy. But it's not going to be a talk about privacy. It's not supposed to be a privacy talk. Privacy is here in some sense of an accident of my personal path. It's also here as a theme, sort of indirectly, because it's a useful constraint that makes us more careful, more cautious, a more thoughtful accountant in various ways. And it's a constraint that plays in interesting ways with some of the other things that we care about. But you don't have to care about privacy. Feel free, every time I say privacy, to think robustness, think stability. These are things that we love about our algorithms for lots of reasons. So if you don't care about privacy, that's fine. Although if you were here yesterday in the boot camp, you probably care about privacy. You're convinced. Similarly, although I'm going to talk about privacy and differential privacy throughout the talk, I'm never going to formally define it. It's not going to be the important issue. You probably saw the definition yesterday, half of you. The other half of you, if you haven't already seen it, again, think robustness, think stability. I'll remind you of the important aspects of the definition when we need them. OK, so what are our 5 stories that we're going to visit today? We're going to talk about sampling and shuffling in stochastic gradient descent. We're going to talk about compression in federated learning communication. We're going to talk about Gaussian sketching. We're going to talk about outlier rejection. We're going to talk about adaptive data analysis. So let's get started. Our first story is about stochastic gradient descent. And you all know and love stochastic gradient descent. And if you were here yesterday, you know a lot about stochastic gradient descent. In gradient descent, just to remind ourselves, what's the problem? We've got some lost surface, and we want to somehow walk down to some global minimum of our loss. Computing gradients on all of the data, which seems like the natural thing to do, is computationally heavy. So typically, we only use a sample of the data on each step. That's the stochastic in our stochastic gradient descent. This sampling adds some noise to our process when you compare it with using all of the data to compute your gradients. But this noise generally cancels out over many steps. Doing the sampling makes things run faster, definitely on each step, but also generally overall. We get better convergence, and it works well. In large data sets, the point is there tends to be redundancy. The important information that's contained in this point is probably contained in a whole bunch of other points in some senses. So the sampling, it just works. And also the sampling, the noise that you get implicitly from sampling, can be helpful for other reasons. It can be helpful, actually, in getting you out of those bad plateaus, bad valleys that you might have found yourself in and popping yourself along. OK. Now, we might, especially if you were here yesterday, be concerned about the privacy of our training data. Perhaps the models that we learn, sometimes on very sensitive, very personal data, might encode some of their training data. Surprise, they do. We have lots and lots of empirical evidence of this, and I hope you've seen this before and you're not surprised right now. But hold on, just a second. Stochastic gradient descent has all this randomness, all that was supposed to be giving us this sort of stability, this robustness. So why are we still doing this? So the problem is that outliers can still have outsized effects. So an outlier, if we happen to sample it for our current update step, can potentially effectively be encoded in the gradient. So if an attacker has access to the intermediate gradients of our SGD, we've clearly got a privacy problem on our hands. But even if not, even if our attacker doesn't have access to these intermediate gradient steps, the fact that SGD is solving an optimization problem yields a lot of information that can be extracted from the final model weights. And even if your attacker doesn't have access to the final model weights, the information that's encoded in those final model weights can often, in some sense, be extracted by clever prompting. And we have lots and lots of nice examples of this, including prompting production models to spit back personal data that they were trained on. And you can get them to spit back near entire copyrighted books. Turns out they're very fond of spitting back basically all of Harry Potter verbatim. So it should be pretty clear that SGD on its own isn't preserving privacy. But there was some randomness there. And it seems like there should be a benefit here to privacy. So not using every point on every round of SGD has a sort of immediate potential privacy benefit, because not every point in the training data affects the gradient at every step. If I wasn't picked, I don't affect it. And so the effect of each point is reduced. And there's a more subtle benefit of this sort of structuring of SGD, and it's in the random sampling. The random sampling has the benefit that an outsider doesn't know which points actually contributed to this step, or this step, or this step. And this can increase the uncertainty that an attacker or an outsider has about the contribution of each point. So SGD doesn't on its own preserve privacy. But it turns out if you add some noise to these updates, you do get a privacy guarantee. What do we need to do in order to get these privacy guarantees? Well, we have to be careful that we don't have these outliers that can dramatically shift these updates. So we've got to do something to fix that. And what that fixing looks like is some sort of clipping, some limiting the influence that any one of these points can have. And then once we've limited the influence that any one point can have, then we can add noise that's tailored not to the worst case, but to this sort of clipped possible influence. That makes things private. And then the cool thing is the interaction with the randomness that was already present in SGD. And it turns out that that randomness that we were just referring to, the attacker not knowing whether you were in or out in a particular update step, that amplifies the privacy that we intentionally added. So the uncertainty from the random sampling allows each point, in some sense, to hide and benefit not just from the noise that was added on them, on their update, but also the noise that you added and you added and you added. So I get a little bit of benefit from everybody's noise. And one of the cool things that this sampling plus amplification does is that in many settings, it basically undoes the harm to privacy accuracy trade-offs that we experience from having to do the sampling. We don't get a strict improvement in our privacy accuracy trade-offs when compared with computing on the full data set, but sometimes we want to sample for other reasons, and it's nice to not have that sampling hurt us. So the sort of side benefit here is SGD's randomness is for efficiency, it's for stability, and it gives us a side benefit of privacy amplification. Our second little story. Our second little story is about federated learning. So for those of you who are here for the semester, you know what I'm talking about. For those who are not hanging out for the semester, the federated learning model is one where instead of bringing all the training data to some central curator who's going to train on all of that data together and sort of call it a single data set, various nodes hold pieces of the training data. And we're going to keep it there. We're going to keep the data at the nodes. Instead of bringing it all together, there's going to be an iterated process of updating the model by querying those nodes. I'm going to come to you with a candidate model, and I'm going to say, based on your data, how would you update this model? And you're going to give me an update, and I'm going to come to you and say, based on this updated model, how would you update it? And then we go back and forth in a structured manner to sort of arrive at the place or approximate the place we would have arrived at if we gathered all the data and trained in a centralized fashion. Now, from that thing that I just described, it should be clear that federated learning induces a heavy communication load due to this repeated exchange of updated models. Many, many works in the field have tried to address the communication overhead in various ways, such as having each user transmit only part of its model updates, sort of sparsification is the key word here, or quantizing the model updates, and sort of trying to figure out various ways to sort of address this communication problem. Turns out, we're often also interested in privacy when we're thinking about federated learning, because important side point, federated learning on its own doesn't give you privacy. It's not a privacy guarantee. It's a guarantee that says that you don't have to pass the data, but that doesn't prevent the trained model from encoding the data that it trained on, okay? So maybe we actually want privacy as well. So we're going to have to add some noise in some sense to those model updates that we're sending back in order to give ourselves some privacy. A number of works have explored interesting ways of getting that privacy in the federated learning setting. You can add noise directly, but maybe you can also get more creative. So there are a couple of papers, these first two here, that look at trying to exploit the noise that's induced when multiple parties are communicating over a shared wireless channel to get sort of the privacy as a side effect from the interference that we have on our shared channel. And this third work here says maybe the same noise can be used to address two needs. One is a compression need, and the other is a privacy need. So they figure out a way to jointly implement lossy compression and privacy enhancement to sort of coordinate these two needs, addressing these two needs together. So part of the message here is that privacy makes sense, in some sense, precisely in settings where there's a lot of redundancy across the data points, where there's a signal to draw out that doesn't depend too much on the data of any one person. And these are also settings where communication may become an issue. There's a lot of redundancy. And so this interaction between compression and privacy, I think, is actually a very natural one. Okay. Story 3. You're given a matrix of data. It's got n rows. Think of each row as belonging to a person. It's got d columns. And when we've got a matrix like this, there are many situations where something we really like to do is multiply it by a random matrix from one side or from the other. If I multiply it from the right, then what I'm doing is a form of dimension reduction. So I've taken this data, again, we've got these n rows, one per person, we've got these d dimensions, and I'm saying, let me project it down. Again, this matrix on the right is going to be, this is our data. This is going to be the random matrix. I'm going to project it down to a lower dimensional space. If I hit it from the left, what am I doing? I'm not projecting the dimension down. I'm doing a sort of data compression. So I retain the number of dimensions, but I reduce potentially the number of data points. Okay? So let's talk about each of those in sequence. Hitting our matrix from the right by a random matrix projects our matrix down, an operation known as Johnson-Lindenstrass transform. The key result here, the main idea to keep in mind, is that this embedding of these high-dimensional points into a lower dimensional space has the nice property that it nearly preserves the distances between the points. It has applications all over the place: compressed sensing, graph embedding, natural language processing, you name it. We love this ability to take something high-dimensional, make it less so. It turns out that this Johnson-Lindenstrass projection also preserves differential privacy, since each point essentially is randomly transformed in this projection process. No other noise is needed in order to get privacy for free when you do this transformation. And there's no reliance here on any special properties of the data. Okay? If we hit our matrix from the these are reference. If we hit our matrix from the other side, then what we've done is we've compressed our data sample, which is useful in many settings, for example, in settings where computer storage is costly. This form of compression of our sample is particularly valuable in machine learning settings that rely on doing various inner products, A transforms B, B's for matrices A and B, because now we can do this sort of sketching, this compression to both the A and the B, and we'll largely preserve these inner products that we care about. So this is a convenient form of a compression for us. It turns out this idea is also compatible with differential privacy, but notice you don't just get the privacy for free when you hit the matrix from this side. Why not? Well, intuitively, imagine you're one of the rows in this original matrix, and all the other rows are zeros. What privacy benefit do you get from being mixed with a bunch of rows of zeros? Nothing. Okay, so in the worst case, we're going to have to add some more noise to this sort of Gaussian sketch in order to get a privacy guarantee. But if all the other data points were random, you'd get a lot of privacy from being mixed with them. And even if they're not random, if they're not worst case, you probably kind of sort of get some benefit. So there's been a bunch of work on Gaussian sketching and its compatibility with differential privacy and its ability to be used as a tool in differentially private data analysis. And we've been looking at these mechanisms further, giving some new privacy analyses. And through our analysis, one of the things we observe is that the richness of the original data matrix, the thing that you want to compress, is actually sort of what contributes to or controls the success of the Gaussian sketching itself in giving differential privacy. So basically, depending on what you have in terms of a minimum singular value of your original matrix, you can sometimes get privacy for free without needing additional noise. But it depends on the data and the properties of the original data. So this is a situation where all of a sudden we're starting to see, not just sort of randomness reuse, but also maybe we're in a situation that's not so worst case, and maybe we can take advantage of that somehow. So this is randomness for data compression or for dimension reduction supports privacy. And if you have sort of non-worst case richness to the data that you're trying to compress, you can get a boost or even a privacy for free. Okay. Story 4. Suppose you got a lot of data. And you want to do something like clustering on it. Outliers can get in the way of your accuracy. We'd like to take care of our outliers. So this idea of this work, known as FriendlyCore, is sort of a smart pre-processing filter. It does outlier rejection on your data set before you run your calculation, your clustering it, or whatever it is you want to do. What's the idea here? We're going to have a notion of a friend. The algorithm is going to look at your data points, and it's going to define a friend of a data point as another data point that's close to it in some relevant distance metric. And then we're going to do a filter across all of our data points. We're going to check every data point to see if it has enough friends in the data set. If the point is kind of surrounded by a bunch of other points, it's going to have a lot of friends. If it sits in a dense region, we're going to keep it. If you come across a point that's an outlier, it doesn't have enough friends, it's kind of far away from the main group, it's going to get removed. So we do this pass. The remaining subset of points that you end up with is called the core. These are sort of friendly points. And then you run your standard computation that you wanted to do anyway, but just on this core. This outlier removal process can improve the stability and accuracy of your computation, and it has demonstrated empirical benefits. The twist of this idea is that you can do this filtering process to figure out who you're going to keep in terms of their friendliness in a privacy-preserving fashion. And this is going to ensure that the choice of who to remove, the act of removing these outliers, doesn't accidentally reveal too much information about the particular points that were in the data set. So by using this sort of private version of filtering, you can guarantee that extreme outliers are generally going to be removed before we have to figure out how much noise to add for privacy. And this lowers the sensitivity of the subsequent computation. So whatever we wanted to do later on, that clustering or whatever we wanted to do, if we started out with arbitrary outliers in our data set, then in order to do that later thing, that clustering or whatever it was, we would have to add noise that would hide the outliers, which in the worst case could be unbounded amounts of noise. If we've done this pre-processing to remove outliers, and we've done it in a privacy-preserving fashion, now all of a sudden we can rely on the absence of outliers. And the amount of noise that we need for privacy can be greatly, greatly reduced. So this is an amazing change. In particular, it allows us to move from potentially dealing with these kind of unboundedly bad points, these really extreme outliers, to being able to handle them and do whatever this sort of task is that we had at hand. Traditional methods for handling outliers often really struggle when your data has a lot of dimensions. This also is a kind of dimension-independent approach. And it can allow us to aggregate updates, for example, from users in federated learning in a more robust fashion. So the point here is that outlier rejection increases accuracy, it increases robustness, and it also can improve privacy by making data non-worst case. All right, story 5. The starting point for this story is that science on a sample works astoundingly well. What do I mean by this? I mean, data-driven science sort of has this mental model that there's some underlying distribution in the world, but I can't access the distribution. When I do science on a sample, hopefully draw an IID from that distribution that I care about, and I would like the conclusions that I draw on my sample to have implications for the true distribution in the world. And the kind of astounding fact that we just ignore, I think, in our day-to-day, but we should stop for a moment and appreciate, is that a Chernoff bound and a union bound together tell us that we can answer a number of queries on our sample that grows exponentially in the sample size, and get a guarantee that with high probability, all of the answers that we get on our sample are simultaneously good with respect to the underlying distribution. Science on a sample is just astoundingly powerful. At the same time, science is an inherently adaptive process. What do I mean by this? I mean the questions that we ask today, the scientific questions that we investigate, are often chosen based on things we learned yesterday or the day before. We notice a pattern in the data, we go and we explore it. We read a paper about some cool new observation based on some shared genomics database. We get some inspiration for some study that we want to go and run on that data set. We identify promising variables, and we go and we leverage them and we evaluate their performance. And adaptivity is great. It's fundamental. It's necessary. Adaptivity, intuitively, is what allows us to do science efficiently, because it lets us pick today's hypothesis based on things we've learned in the past. If we didn't have adaptivity, the way we would do science is just to ask all the questions in no particular order. This would not be very effective science. So we love adaptivity. We want it. At the same time, adaptivity can lead to disastrous overfitting. It makes all of those beautiful statistical guarantees. I just said science on a sample, it's amazing, exponential number of queries. It makes all of that go out the window. Because as soon as you're picking your queries in an adaptive fashion, after you've answered one query, you have no validity guarantees over the next query if you pick it adaptively. We went from exponentially many queries to one query. This is very bad news. It says, basically, you can't reuse data if you want to think in between your uses. This is like sobering. And it's not just some like totally abstract theoretical phenomenon that I'm talking about here. Maybe you've noticed that the data-driven sciences have been kind of having some trouble in recent years. You've heard about these, failures to replicate a very high-profile experiments. You've heard about the statistical crisis in science, however you want to call it. And there are a lot of things going on here. But one of the things that's going on here is that adaptive reuse of the same data can mislead us. And it can cause us to quickly zero in on quirks of the sample that we're using. And so we make discoveries that look amazing that don't then replicate on a fresh draw or on the underlying data set. See this in theory, we see this in practice. Let's sort of formalize this situation a little bit to make sure we're on the same page about what we're talking about. So the setting is one where we have a database, and there's some query stream that's coming in, and we're trying to design an algorithm that's M that is going to produce responses to these queries. We've got to give answers. We'll get a question, give an answer, get a question, give an answer, okay? And it's going to be based on a sample. We don't have access to the underlying distribution. We've got a sample. So where is the adaptivity in this picture? Well, it's not there yet. The adaptivity is sort of in who's generating those queries. So we're going to put a little box in there. This is going to be the adversary or the adaptive party, or however you want to, there are a bunch of A's that work here. And they're going to get to observe the responses and generate new queries on the basis of this. And so what we kind of want, sorry to make it a little bit more sort of fleshed out, we kind of want to be able to draw this box and say this is a box that, given access to a data set and an algorithm M that we want to use to answer questions on the data set, and a thing that generates questions in an adaptive fashion, this A, we would somehow like the behavior of this box. What's the behavior of this box? Well, it effectively produces answers to questions, question-answer pairs. Like the behavior of this box to be well behaved. What do we really want from this box? Well, we want it to not overfit. We want this box to not cause us to start addressing questions whose answers are very, very different on the data set that we have on hand than they are in the underlying distribution. Because then we're going to get ourselves in trouble. We'd somehow not like to lead ourselves to ask overfitting questions, because then we're sunk. So the question is, how can we do this? This is sort of the question of like, how should we build our pipeline to do adaptive science? So this is the moment where I get to say, differential privacy to the rescue, because a number of works from about a decade ago formalized the realization that the toolkit of differential privacy is also useful as a tool for ensuring generalization in settings where our queries are chosen adaptively. What's the intuition for this? Well, I said, when I say privacy, think stability. What is differential privacy? It's a guarantee that says that the computations we do on our data set should not be very sensitive to small changes in the underlying data. We should have a robustness property. It turns out, if you have this robustness property, what does it mean? It effectively means that the things that you can learn, the things that you extract from your data set, they're kind of aggregates. They're not specific to any one individual. And so this noise that we introduce for the purposes of privacy also effectively prevents us from memorizing too much about the specific data set and tailoring the things that come next, the adaptively chosen queries, too much to the data set. And so we have this really cool sort of literature that says basically all of those things that people have been doing for 2 decades, all of those algorithms that have been generated for differential privacy, they have a new purpose now. You can use them to prevent overfitting in adaptive data analysis. And there are also a number of additional results that kind of box in our hero here, showing that not only is privacy, this sort of noise for privacy necessary, but it's sufficient, but it's also necessary in the sense that the scale of the noise that we need to add for differential privacy purposes is something that we also have to tolerate in the worst case for adaptive data analysis if we want to be able to do our adaptive data analysis in a computationally efficient fashion. And how do you get to results like this? Basically, you cook up these crazy bad crypto encoding data distributions and data sets and adaptive sequences of queries that we can't answer better than with the noise of differential privacy if we want to do it efficiently. But there's something a little unsatisfying about this whole story. And it's that, what if we're adding noise to fight these, but what we face are actually these? Differential privacy is, rightly, a super paranoid notion. It's a worst case notion. It wants to give guarantees against the worst case data distribution, the worst case data set you could have on hand, looking at the worst case possible output that your mechanism could generate with the worst case possible query that you have to answer. This is worst case all over the place for good reason. We want privacy for the weirdos and for the outliers. We want worst case. But we're not doing privacy here. This is not a story about privacy. This is a story about adaptive data analysis. And for statistical guarantees like generalization, we only really need statements that hold with high probability with respect to the sampled data set, and only on the actual queries that get issued, not on the worst case queries that nobody ever asked. So differential privacy dictates noise that's going to need to scale. For example, if we're doing numeric queries here, it's going to need to scale with the range of the queries. So the worst case, we're going to have to scale our noise accordingly, even if, in practice, we have highly concentrated queries. So there have been a number of works that have tried to step us away from this worst case in the context of adaptive data analysis. Sometimes they look like specialized mechanisms. We also have some work showing that Gaussian noise addition actually can be tailored not to that sort of worst case range of the queries, but just to the standard deviation instead. So we can potentially get much, much better guarantees. So on the one hand, this is a lesson that randomness for one purpose gives us other benefits, but it's also a lesson to be careful not to assume the worst case if you don't really need it. So noise for privacy prevents adaptivity-driven overfitting, but for adaptive data analysis, we don't care about the worst case. And you can often add noise that's far less than the worst case. So we've gone through this series of sort of 5 different stories. And there will be these sort of repeating themes as we go along. We talked about stochastic gradient descent and how it sort of aids privacy with this amplification. We talked about how compression and federated learning for the purposes of reducing communication can give you privacy for free. We talked about how dimension reduction can give us privacy and how sample compression sometimes gives privacy, but the guarantees that you get depend on some non-worst caseness of the data that you have at hand. We talked about how outlier rejection makes clustering more robust, but also more amenable to privacy by getting us away from worst case data. And we talked about how privacy gives us protection against adaptive data analysis, against that adaptivity, but that it's actually overkill. And we talked a little bit about how we can actually add less noise that's tailored to the non-worst caseness of the queries on the actual data. So running through all of this were these themes of randomness is showing up in lots of processes for lots of different reasons. It has so many different roles. And one of the things that happened here is in every case there was an observation that randomness for purpose A can also be beneficial for purpose B. So that's sort of theme 1, is that the thing you care about, whatever it is, there's some randomness there, right? Let's think a little bit about what else that randomness is doing for us. The other theme that didn't show up everywhere, but I think is still a prominent one, is this idea that we know how to do the worst case analysis. We're really good at it, but sometimes it's not the thing we care about. And trying to figure out what does it mean to get away from the worst case? What does it mean to model something that's not the worst case? How do we give guarantees that aren't driven by the worst case? And I think the sort of interplay of these 2 themes is this sort of powerful lens for trying to understand lots of different problems that we face today. So as I promised at the start, there's no glorious new theory here. This is old ideas repackaged and sort of revisited, slowly, sort of modestly chipping away at these little gaps that we have between theory and practice. As promised, I said privacy, privacy, privacy all the time, but this is not a story about privacy. Privacy is the lens through which I see a lot of things, but this is a story really about squeezing out every last bit of the randomness that we have and not letting the worst case get us down. I think federated learning and the framing that it gives us sort of inspires us to think similarly about specific structures, specific goals, specific challenges for our learning. We have the communication overheads. We have questions about computation. We have questions about trust. We have questions about privacy that come together really nicely in this framework. And I think that these constraints and these goals are very amenable to this kind of framing, these kinds of looking at compatibilities, looking at the rules of randomness, looking at these types of analyses that I discussed today. I really enjoyed being here with you today. I'm excited for you all who get to spend the semester together. I'm really looking forward to seeing what you all accomplish. Thank you. And I'd be glad to take questions.
I think we should probably pass this around.
Fantastic, thank you. You're first.
Great talk. Thank you very much. So in your sketching part, you mentioned Gaussian sketching. And the community is that uses it in particular for randomized linear algebra is moving away from Gaussians because they're much more expensive and using much cheaper, even sparser distributions because the answers are just as good. So I'm wondering how many of the properties that you like would get lost by switching to a non-Gaussian sketch?
It's a great question and one that I don't have a comprehensive answer to, but it's sort of there on the... It's there on the horizon as a great sort of next question in this line of work, as sort of what are the consequences of changing the various properties of this random matrix that you use. In some sense, hitting your data matrix with a random matrix summarizes a lot of things that we do for differential privacy purposes in a lot of different ways, and I think there's room to play with other forms and other structures of that matrix and to sort of discover their properties. But I don't have a comprehensive answer. It's a great question.
We're building a library called the Randomized Laws, and it will have a lot of different random distributions in it.
Fantastic. OK, I love references. Thank you. OK.
Are there other questions?
Thanks so much, Katrina. I was wondering how you like to think about how to model average case assumptions. Like, you don't have really worst case queries in the adaptive data analysis. How do you decide what's a good choice and for which you get better error? And similarly, for the Gaussian sketching, how do you decide, okay, what do the other data rows look like, which are going to hide the person well enough?
Yeah. So I like that question. If I had a better answer to it, I would have a lot more papers. So in the context of adaptive data analysis, we have this theory that tells us exactly how adaptivity, leads us astray. It says in order for adaptivity to lead us astray, you've got to encode too much information in the answers to your queries, and then you got to go leverage it to ask these overfitting queries. And that, that's something that we can write mathematically and formally. And so that should be, a message to us about where do we look for non-worst caseness, because it says effectively, if your queries are not such that they leverage the information that's encoded, even if it's there, you're not going to get into trouble. It also says if you don't encode too much, you're not going to get into trouble. And we've so far, as a literature, spent more time on the don't encode too much, which is what this sort of differential privacy intervention is doing for us, and less, although Vitaly and others have thought about this, less about what does it mean to be asking non-worst case queries. And it's not for lack of trying, at least on my part, but I really like the question. I don't have a good answer to it, but I want to see people making progress on that. In the context of the Gaussian sketching, I don't feel like we did any thoughtful or intentional modeling of the non-worst case. The properties of the data that end up giving you guarantees in some sense just popped out of the analysis. But it wasn't that we came to the problem and said, well, this is a reasonable assumption to make about our data. Let's go see what it gives us. But you could do that. You could come and say, hey, I'm willing to make the following assumptions about my data and the structure that it has, or the sort of randomness that it has present in it, or I would be really glad to get better guarantees in this following setting. Let me go try to leverage it. It's not what we did there. So I haven't done that kind of thinking in that context. But yeah, it's a good question.
So this may not be the main point of your talk, but does the process of outlier elimination impact the privacy of the data you leave in the data set?
So that's a really, really important point. If you don't do your outlier elimination in a privacy-preserving fashion, then you're in trouble. And you can't get the overall privacy guarantees that you want. And that's an interesting subtlety, because it sort of feels like it shouldn't be such a big deal. But if you want to do end-to-end privacy analysis, you've got to account for the privacy of that first step. And it turns out you can do good outlier elimination in a privacy-preserving fashion, but that's something you have to work for it. It's not sort of immediate.
Yeah, thank you again for the great talk. What I wanted to ask you is the flip side of the price of privacy that we might actually incur if we really care about privacy. For instance, if we want to learn under privacy constraints,
Yeah.
so I think it was also results that show that it's going to be much harder, right? And what are your thoughts about, like, you gave us 5 nice stories. Are there like also 5 horror stories on there?
There are more than 5 horror stories. Yes, so it's interesting. In some sense, all of the study of differential privacy is a story of trade-offs. It's a story of what can we achieve in terms of privacy, accuracy, quantity of data, is sort of how I think about it. Because everything's a trade-off here. There are fundamental limits to what is possible in terms of these trade-offs, and it's been this sort of dance of how close can we bring these together. And part of the sort of backstory is, and how does that compare with a non-private version? There are situations where introducing privacy as an additional constraint comes basically asymptotically at no further cost. The problem is so compatible with privacy that it's basically privacy for free up to the asymptotics that we like as theoretical computer scientists. And there are other settings where something is possible without privacy and impossible with privacy, and things look incredibly brittle. I don't think we have a clean, clear, beautiful, overarching story that helps explain why some things are the first category and why some things are the second category. And we got all the other things that are in between, where it's just privacy makes things worse, somewhat worse, and sometimes we understand it well, and sometimes we don't yet fully have the picture of how much worse things get. So this is still something that's sort of under investigation, is understanding what is the unavoidable cost of privacy protection as you incorporate it into machine learning. Sometimes it's great, sometimes it's disastrous, sometimes it's in between, sometimes we don't know yet. But we see from the folks who are actually in the trenches, there are folks here in the room who are working in real companies that actually really implement these things on real data, is one of the challenges is, yes, privacy comes at a cost, but more than that, in some sense, is that even once you manage to get privacy sort of up and running, because you're in a great situation where it's kind of compatible and you've got a whole lot of data because you're a Google or Apple of the world, that the levels of privacy guarantees that we sort of succeed in getting while getting satisfying accuracy don't read off as meaningful guarantees. So the parameters that end up getting used look really, really bad. And there's sort of this gap in our understanding to sort of say when that's just because the guarantees were actually meaningless. I don't think that's always the case. I think that's often the case that we're doing something that should be meaningful for privacy, but we don't yet know how to say that it is, because we don't live in the worst case is part of the issue. But we don't always have the vocabulary to talk about it.
Thank you.
Yeah.
I have a few questions. First, in the spirit of your talk about not focusing too much on the worst case, should we drop the word guarantee and adjust to something else, understanding that it's just not going to be guarantee, but it improves?
Well, I don't understand what it means to drop the guarantee. I still want to do theory. So I still want to prove things.
Yeah, improves robustness or something else, but guarantee just kind of... Anyway, just wanted to hear your thoughts that you would prefer to use guarantees.
I don't know, maybe I'm just used to the word, or maybe I don't understand the implications of getting rid of it. But it still feels pretty useful in my vocabulary.
Yeah, okay. Yeah. Like Rainy and other models, they seem to say like, okay, we won't guarantee, but we will improve. But anyhow, second question is that what do you think will make the adoption easier? There's a lot of data sharing that takes place between large companies and so on, but it's missing. The implementation is kind of not there.
Yeah.
So what would make it fly? And is that people who are implementing today are their own worst enemy by making it sound very complex and so on? And then it's just they will implement a good job on one project in one release, and after few quarters, it's just outdated. Use cases have moved on. So what do you think will make it more?
That's a great question. I mean, there are other people in the room who've actually worked on this question, maybe better qualified to answer it than I am. I mean, you point to a bunch of the challenges, I think, very accurately. There's this, you need specific expertise in order to implement. You were talking about sort of the success of privacy tools. You need specific expertise in order to implement it. That we don't have off-the-shelf tools, although many folks have tried to push in that direction. Many projects have tried to push in that direction. There's a sense in which you have to solve each problem separately. I mean, privacy is a different challenge in this setting than it is in that challenge, or maybe you have a different algorithmic toolkit that you want to deploy. So I think you're pointing to a lot of the challenges. Other than the obvious answers, I don't think I have anything, surprising insight, but I'm curious if somebody else has an insight to offer. Adam, it looked like you were going to offer an insight, but no, it was just an arm. I'm curious if anybody else has a good answer to this question about, what else should the community be doing, where community is, broadly defined, in order to drive successful implementation. I think the obvious things are certainly better, off-the-shelf solutions, and we also have to keep doing more theory that will sort of bridge these gaps and help people understand, what are the privacy guarantees that they can achieve in what settings, and helping us get these better trade-offs, better privacy accuracy, better transparency, absolutely. Setting standards where people are actually implementing these things and talking about them, and there's some degree of, sort of belief that what is supposedly happening is actually happening behind the scenes, auditability. These kinds of questions I think are all relevant. None of them sort of nails it.
I should say the two things that are encouraging is that the Google BigQuery and so on, they come pre-built now with examples. If someone wants to build a program under official privacy. And then this court case in Alabama was also very good. Census Bureau fought back.
Yeah.
I see a lot of questions. I'm going to try to take three. One here.
Yeah. Thank you very much for the talk. I have a question regarding the adaptive data analysis. So does it make the analysis any simpler if we know that only the final query result is going to be released?
If only the final query result is going to be released. Well, we still have the concern that the final query is going to be chosen as a function of all of the things that happened before. So we still have to get ourselves to not be in a situation where the choice of that final query overfits to the data set. Because once that, that final query that we pick is chosen so that it gives, one answer on the data set we have at hand, with the true answer on the underlying distribution is something different, we're kind of in bad shape. But if we know, for example, that our process is going to have sort of limited memory, and we're not going to carry forward all the things that we extracted from the data set up until now, and that we have limits on how much we can encode about the data set because we're carrying very few bits from query to query. We can do various things that can sort of make it so that we're not just accumulating all of the information about the data set and then potentially leveraging it and picking a devastating final query. But just saying that it's only the final query that gets released doesn't really save us on its own, but it's maybe part of an approach.
I'm going to take two more questions, one Adam here and one there, and then we'll thank Katrina.
Sure. Okay, so I was actually intrigued by your statement, we still want to do theory.
Is that so surprising here? What is this place called?
I don't disagree with the assertion, but I want to ask what one means by that. And specifically, if I think of the distinguishing, the things that theory contributes, they are sometimes proofs.
Yeah.
Right? But there are at least a couple of other major contributions that the theory research on a topic does. One is sort of definitional, just formulating problems clearly.
Yeah.
But even refutable statements that we don't know how to prove, but refutable like conjectures, can advance things a lot. And I would say our community has done really well on definitions and on proofs, and maybe like is a little cautious about advancing, you know, unproven conjectures. You know, we kind of have a culture of like, kind of, you know, like thinking of them more as open questions, of course, which they are. But I wonder if there's sort of something to be said to sort of taking a little bit more of the physics approach of, let's say, the best parts of it, which are to, you know, to formulate statements that could potentially be refuted, that we actually genuinely think are true, that aren't like obviously false, and that could drive forward, you know, and sort of like assign more value, give more value and credit to people who come up with good statements of that form, even if they're not, they don't right away come with a proof.
So bring the culture of crypto to other areas. Maybe. I like the suggestion.
So you've shown us many examples in which we can go haywire in analyzing data. And so I was trying to think of a public example that everybody knows about, and that is election polls. And so we take a sample and we predict the results of the election. And lately, at least in the United States, the projections have been wrong. So within your framework, where was the mistake? What went wrong?
So I'm not an elections expert or polling expert, but my understanding is that a bunch of things are going wrong here. I mean, we are not sampling IID for lots of reasons. We have incredibly low participation. We have limited tools to try to back ourselves from our biased sample back to a representative sample, and they're not working for us. We have people not telling us the truth about their plans. A lot of things that I don't know how to do any theory about. But I like the example. I think it's a good motivating example because I think the non-IAD challenge in particular.
Can you define IID?
Oh, sorry. I just mean if we have a distribution, are we taking just independent draws from that underlying distribution? And in the polling situation, no. We're getting a bias towards some pieces of the population versus others when we do our polling for various reasons, whether it's because there's some people who, you know, have phones, some people who answer the phone. There's really interesting work in the field of polling and surveys looking at trying to undo some of the bias that comes from the fact that the number of times I have to call you in order to get you to pick up is not independent of the content of your answers to my questions. So there's a lot to be done there. I don't know how to do good theory about it, but I like the non-IED question. I think it's a nice framing that probably can inspire some good work.
Well, thank you all for being here, and thank you, Katrina. Please join me in thanking her once again for